Good morning, everyone. I'm Cindy from SuperMap International Department. It's a pleasure to be here with you today, and thank you for taking your time to join me. Today, I will introduce the technologies of SuperMap 3D GIS. SuperMap has been at the forefront of GIS development by establishing 6 core technical systems that drive the evolution of GIS foundational software, collectively known as the BRT-IDC framework. Among these, one of the key focus areas is the new 3D GIS technology, which I will be introducing to you today. Let's start by taking a look at SuperMap's 2D and 3D data models and its modeling capabilities. SuperMap supports a wide range of 2D and 3D spatial data models, mainly in 3 categories: object models, including 2D and 3D points, lines, polygons, and bodies, and network models covering both 2D and 3D network data, and field models such as 2D teams and grids, and 3D models like team and voxel grids. Different types of 3D model data are suited for different application scenarios. Let's first look at what kinds of applications can be supported by the object models. SuperMap supports a wide range of object 3D models, including detailed macro models built with tools like 3ds Max, as well as micro-level build information models. It also supports the construction of 3D body models to represent discrete or homogeneous solid objects, which can be exported as 3D model data or even used for 3D printing. And SuperMap also supports geological body modeling using boundary representation. This allows for integrated visualization or layered display based on geological types, making it highly effective for geological survey and analysis. Digital twins are widely used in the water conservancy industry nowadays. However, it's still challenging to connect them with professional simulation models and fully integrate accurate results into real 3D scenes. But with our 2D and 3D data models as a bridge, SuperMap can overlay simulation results from tools like Dassault's XFlow, expanding the use of scientific simulations and giving 3D spatial systems a more professional and intelligent core. Besides importing model data, SuperMap also can create models automatically using oblique photos and AI techniques like classification and detection. It identifies building areas and roof types. It can then regularize building shapes and extracts building heights automatically. And based on various SuperMap built-in material types, vector data of building footprints, roof types, and building heights, we can quickly generate building models with just one click. And with this modeling capability, we can rapidly create city-scale building models. In this example, we can say diverse building types and roof styles across a 35 square kilometer area with over 5,300 individual models. building such a large scene manually would be extremely time-consuming and labor-intensive. However, with our AI-powered modeling, it takes just 20 minutes. And for city-scale models, roads are another essential element alongside buildings. A SuperMap platform also supports intelligent 3D road construction based on road satellites, road classifications, and lane information. We offer a wide variety of road styles and types, including intersections like cross and T junctions, and the platform also supports sidewalks, zebra crossings, various directional areas, and traffic markings that vary according to the road classification. In addition to AI-powered building modeling, we have introduced AI-based point cloud instance segmentation for the power industry. This technology automatically performs semantic segmentation on categories like polars, power lines, vegetation, and ground. It can also extract individual polar and power line objects, achieving precise instance segmentation of point clouds. For point clouds with around 3 million points, the inference time is about 44 seconds, significantly reducing manual labor costs and improving post-inspection efficiency in power grid maintenance. Based on these 3D models, we can perform various analyses, such as visibility analysis, skyline, viewshed, and shadow rate analysis, and so on. The platform not only generates these analysis results, but also allows us for exporting them. For example, the skyline height restriction model serves as an essential tool in urban design approval, helping control building heights to preserve cityscape harmony. Next, let's take a look at the 3D applications SuperMap can support based on the network model. 3D network models are mainly used to represent connections between objects. Between objects such as pipelines, tunnels, and valves in utility networks, as well as transportation network. SuperMap allows us to combine pipeline attribute data with symbol models to customize various types of manholes and covers, enabling large-scale tailored urban underground pipeline networks. If a pipe bursts, the built pipeline model enables burst analysis to help officials quickly locate the break and identify which valves to close, improving response efficiency. It also supports upstream and downstream tracing to help users quickly determine the affected pipeline areas. Next, let's take a look at field models. SuperMap's work cell grid technology breaks 3D space into small units we call work cells. We can attach work cells to models for work cell-based analysis, while different colors represent signal strength. This allows simultaneous analysis of vectors like building obstruction and terrain variation, enabling precise identification of signal blind spots that traditional methods often miss. This greatly improves the efficiency of 5G network optimization. And our voxel grid model can also integrate with simulation results from Dassault to dynamically display stress distribution and deformation of bridges under vehicle loads. It can highlight areas where displacement at key points exceeds safety thresholds, helping engineers develop effective reinforcement plans. Okay, next, let's take a look at SuperMap's capabilities in processing multi-source 3D data. Over a decade ago, we began integrating various types of 3D data. Today, our data management capabilities cover a wide range of 3D data types, including terrain, image, oblique photos, point cloud, pipelines, and so on. SuperMap can integrate this data into our platform, and then we can process and fuse them to enhance each other for more informed decision-making in urban planning, infrastructure development, environmental management, and so on, by providing a realistic, detailed representation of spatial environments. For example, we can overlay real-time video streams on terrain and imagery data, enabling smoke and flame detection to improve the efficiency of forest fire response. In addition to supporting full dataset integration, SuperMap also enables partial data updates. For oblique photograph data, it allows updates within any area, greatly saving time. It also supports seamless switching between old and new data versions. This slide shows a comparison before and after a local update of the oblique photograph data. As you can see, only the selected area was updated without reprocessing the entire dataset, saving significant time and effort. And for fine grid model data, SuperMap supports updating data based on bounds or by objects. We can define the update bounds, and the data and attributes within the specified bounds will be updated. Alternatively, we can provide specific object IDs, and then the corresponding objects and their attributes will be updated. And also these features are applicable to our beam tiles. In this video, we can see that we will define an update bound. The data within this yellow polygon will be updated. Using the model tile local update tool, we only need to specify the original data and the updated data, and then the system will update the data accordingly. Okay, after introducing the data model and the integration of 3D data, we recognize that the sources of 3D data are diverse, which leads to a widely variety of 3D data formats. Next, let's take a look at the standard for 3D tiles. The Ministry of Natural Resources of the People's Republic of China, in collaborations with our SuperMap, has established the industry standard for the data format for spatial 3D model tiles, which officially came into effect on November 1st, 2023 year. This tile standard is derived from the OSGB format, inheriting its advantages such as openness and support for large data volumes. It also addresses the limitations of the OSGB format, supporting passing on WebGL clients, enabling monolithic data representation and accommodating multi-source data. Compared to 3D tiles, as 3M and 3D tiles has many similarities in their design, but as 3M supports a wide range of data types and comes with more comprehensive supporting tools. We also support converting R3S format tile data into our S3M tiles. And currently, more than 20 modeling software tools support the S3M format, including photograph modeling software such as Bentley. These developments greatly enhance the sharing and the utilization of 3D data. We know that in addition to the management capabilities of 3D data, rendering is equally crucial. When the rendering performance is high and the results are visually appealing, it captures the attention of our users much more effectively. SuperMap supports rendering 3D data with physically based rendering, short for PBR, materials. By using PBR materials, our models exhibit a much more realistic appearance, with enhanced details such as overall lighting and metallic textures. SuperMap also supports the use of ambient light. After applying the ambient light effect, the model's overall lighting and finer details, such as reflections on glass walls, show significant improvement compared to standard materials. As mentioned earlier, high quality rendering is essential for captivating users. This video showcases how we were effectively and realistically displayed the final model of the Shanghai Oriental Pearl Tower and its surrounding buildings in SuperMap's desktop software with impressive detail and visual appeal. And this slide shows the rendering of 3D data in a browser using SuperMap iClient for WebGL. The left video demonstrates power pulse shift with the interplay of light and shadow, as well as the flow of electricity along the power lines. And the video on the right highlights the flowing water surface with reflections of white clouds, creating a visually stunning and realistic effect. Since 2020 year, technologies like digital twins, the metaverse, and XR have evolved, raising the need for better visualization. SuperMap launched the Hi-Fi 3D SDK, combining GIS spatial management with game engine rendering, empowering 3D digital platforms for applications like digital twins. Here, we showcase the effects of daylight light penetration using the game engine, including the lighting and shadow effects on the ground, grass. Additionally, we highlight nighttime city building, lighting, water reflections, and the visual effects of fireworks blooming. By integrating this GIS data with game engine technology, we can perform a variety of spatial analysis. This analysis not only improve spatial understanding, but also can aid in making informed decisions across multiple industries, such as counter analysis, visibility analysis, spatial query, and BIM cross sections. Not only can our GIS data be used within the game engine, but we also support integrating existing data imported into the UE platform. You can combine your data with S3M datasets within the same project, enabling seamless participation in various spatial analysis. This is the end of my presentation. Thank you for your time and attention. Thank you.